Let's get started. Couple of organizational matters. You'll see a slide about lunch on the right-hand side and a slide about the conference dinner, and it seems that the cutoff is at noon today for notifying your attendance. And finally, I've been asked to remind the poster presenters that the poster boards are available in the room next door for putting up the posters, and to remind everybody that at, when is it, at 4:30 this afternoon, we have a session where poster presenters can give a brief oral introduction to their poster, and so I encourage you to attend that. Okay, so we're now pleased to welcome Ursula from Dortmund to speak to us about dimension reduction.
Okay, thank you very much. And well, I would also start by thanking the organizers for this wonderful workshop, and it's a real pleasure to be here, and I feel honored and pleased to be able to give a talk to you here. Well, the very short title is Dimension Reduction, and of course I'm not speaking on this topic in this generality. I have made it a little bit more detailed. So let me give you a short overview of what I will be talking about. I'd like to start with a description of the situation in multiple regression where the predictor is high dimensional and the response is univariate. And I'd like to show you a couple of approaches to cope with that situation. Then I would come to the well, more detailed topic of reducing the dimension of the predictor with certain methods. And there are a couple of those around, namely sliced inverse regression and a robust version of that called DAME, dimension adjustment method. Then I'd like to come to the more special situation of variable selection, which is of course also a kind of dimension reduction. And I'd like to review the new method called EARTH, introduced by Hel Doksum, and an even newer one just introduced by Jin-Keng Fan called THIS, and I think that had been mentioned already by Peter in his talk. Okay, and I'll conclude with a short outlook. So what is the situation? We are confronted with data, and these data are assumed to obey a very general model. There is a link function f, which links the high dimensional predictor x with some univariate response y. And of course it is the goal to, well, to find the link between the predictor and the response, but this is difficult whenever the predictor is high dimensional, and that's just because of the well-known curse of dimensionality, which makes it impossible to, well, to use these usual nearest neighbor techniques, because in high dimensions, around every point, in each neighborhood of every point, the data is very sparsely available only. So nearest neighbor techniques do not work. And that's the reason why one needs to reduce the dimension of the predictor, right? Well, this is well known, and of course we are confronted nowadays with many situations where the dimension of the data is high, especially in life sciences, of course. So what is available? There's a couple of approaches available. Firstly, these approaches mentioned here are methods which at the same time reduce the dimension of the predictor and estimate the link function, like projection pursuit regression, for instance, and Mars, introduced by Friedman, and so on. So this is different from what I mentioned here, namely in a first step, one can try to reduce the dimension of the regressor variable of the predictor, and then knowing where the link function lives, in which lower dimensional space, you do estimate it in a second step. Okay, well, of course one can think of a very simple approach in that sense, namely just do some principal component analysis of the predictor space. But that would not make any use of the information sitting in the data between the connection of x and y. And that's why some other methods have been proposed which make use of that information. And that is especially the method SIR, called sliced inverse regression, and more sophisticated versions of that, which I have just written down here, which can cope with some deficiencies SIR shows up, namely when the function shows up too much of symmetry, for instance, then it is difficult for SIR to estimate the direction in the x space where you find the highest variability of the function f. And that's why other methods which are based on higher moments have also been introduced. Okay, so let us look at that situation a little bit more concretely. So, as I said, a very general model. Well, this is a very general situation. You usually think of an additive error term, of course. And one assumes in the dimension reduction task that, in fact, we are in a simpler situation, namely in the situation that there is a link function g which lives on a lower dimensional subspace of Rd, and that there is some matrix B which projects x, your variables x, into this subspace. Okay, so these vectors which constitute this matrix B are called the effective dimension reducing directions. Okay, and they span the so-called central subspace, or sometimes called central mean subspace. And of course, in this model of dimension reduction, it is the goal to estimate this space script B, which is spanned by the effective dimension reducing directions. And well, there is a couple of approaches to do this, to estimate this space B. All of them, or almost all of them, start by finding some vectors Vj which already lie in this subspace, then combine those to some matrix M. Okay, well, of course, then the span of M is in this subspace B. And one goes on by extracting the eigenvalues of this matrix, finding the corresponding eigenvectors, and, well, the span, so to speak, of these beta 1 to beta k's, they are used to estimate the subspace script B. Okay, so methods now can differ in how you constitute this matrix B, how you find it. And, well, there's moment-based methods. First of all, there is this method SIR, which I have already alluded to. And SIR, sliced inverse regression, takes the covariance of the conditional expectation of the predictor given the response. And that makes sense because under some regularity conditions, this conditional expectation lies exactly in the dimension reducing subspace B. Okay? And well, as I said, if there is too much symmetry in the link function, then one goes to higher moments, such as covariances and so on. And the principal Hesse directions also is second moments, and there are also methods which use third and even fourth moments. And some of them are only intuitively explained, and well, asymptotics of those methods isn't always known. Okay, so there is also adaptive methods where this matrix M is found by gradients. So you try to find the gradient of f and look for a direction of steepest ascent or steepest descent. And that is done, well, usually based on Fourier expansion. and so on. One can also take weighted gradients. So this is all possibilities to find the matrix M. It can also be done by using local linear regression, like in MAVE, which is an abbreviation for minimum average variance estimation. So there are quite a few acronyms in my talk, but they have been invented by all of us. Okay, so another possibility is to maximize the correlation of these terms simultaneously. And there's also the possibility to not estimate B, but find vectors in the orthogonal space of script B, combine those to a new candidate matrix, and then, of course, you have to look for the eigenvectors from the smallest eigenvalues. Okay, so this is just all possibilities, and as robustness is one of the topics I work on, there is also I'd also like to give a hint on robust methods which are available in these circumstances, and I'll definitely come back to this point later. There is robust versions of almost all of these methods, and there is a reason why they have been constructed. Okay, so to get an idea of how these dimension reduction methods work, I would like to explain it at the, kind of first one introduced by Lee, sliced inverse regression. And I really think that this was an intelligent idea to make use of the information sitting in the data of how X and Y are related to, just in order to reduce dimension. Okay, so what did Lee suggest? A first step is a very usual one. You just standardize your X observations, and then you look at the ordered Y values and kind of put them into slices. And then for each element within each slice, you go down into your predictor space and collect the X corresponding X values belonging to the observations in a slice. Okay, so you get like this also corresponding X values for each slice. And for each slice, you calculate the mean within the X space of the X observations. And those means give you the matrix M then. Okay, so I said X values, but of course this is standardized X values. And like this, you can find the means of the corresponding Z values for each slice. And those form your matrix M. And for this matrix now, you calculate the eigenvalues and also the corresponding eigenvectors, which then, a little bit normalized, give you the estimates of the effective dimension reducing directions. And thus you have estimated the lower dimensional subspace B on which the link function has, one can put it also like this. This is exactly that subspace and that direction where the link shows up highest variability, right? Okay, so this is shortly a description of SIR. And as I said, there is also robust versions around, and I should explain why this seems to me to be necessary. Well, as dimension reduction is a like pre-step in data analysis, of course you shouldn't be too much suffering from outliers or contamination. So this is a short sensitivity analysis of SIR. Though, as I said, I really find it intelligent, but it remains intelligent because there is a very simple remedy for what happens here. If you just take one out of your observations, and for the X part, you contaminate this by shifting this X observation into some direction, say beta tilde. And you do this as far as T tells you? Then there is a theorem which tells us the following. If you then proceed with the SIR procedure for the contaminated data, then what happens is that under some really weak regularity conditions, the further out you push your X observation into the direction of beta tilde, it happens in the end that the estimated direction becomes almost orthogonal to the direction in which you have shifted the X observation. Okay? So that means that if you have only one large contaminated X value, then in the end it can happen that the estimation of the effective dimension reducing directions are almost orthogonal to the true one, because of course you can choose beta tilde to be the true direction, as this picture shows us. So this is from simulations, and the high dimension D is only equal to 2 here. K is 1, the lower dimensional dimension is just 1, and say beta 1, that is just the correct, in our situation, dimension reducing direction. Say if these are your X observations and you put quite a few into the direction of the true dimension reducing direction, then what happens when you estimate, you want to estimate this direction by SIR, this is estimated almost orthogonal to what had been correct. Okay, so this is a kind of worst case behavior in a robustness context of this procedure, and that's why it makes sense to help it make more robust, and that's of course very easy because you could just use within every step the robust counterparts of the estimators which have been used within SIR. So instead of using means and empirical covariances, you use robust location estimates and robust scatter statistics. For instance, a multivariate version of the MED or a projection pursuit based scatter statistic based on a univariate, say, Q alpha estimator of scale. And that's worthwhile doing. We have carried out a small comparison by simulations. Namely, this is a very simulation where the link function looked like this, so it depends only on 2 of the X variates, and the dimension of your observations in the beginning had been 10. And what we have been doing is we contaminated one of the X observations by shifting it outwards, and as a performance criterion we have used the canonical correlation between the true direction and the estimated direction. And this is the result. So what is shown here, so this is the original SIR, and on this axis there are the values of the canonical correlation. The best value it can take is 1. So what you can see is when there is always left-hand side is no contamination, right-hand side is under contamination. So SIR is very good, as you can see, for almost all choices of numbers of slices we had been trying out. So if there is no contamination, the canonical correlation between the estimated and the true direction is fine. Okay? But if there is the contamination we have just described, then the canonical correlation is much lower. So these are the corresponding box plots, of course, of the canonical correlations. And if you use robust versions, and we have tried out 2 of them, namely the one where a multivariate version of the MED was used, and this is another one with a projection pursuit scatter estimate based on, well, the ordered values and this Q alpha introduced by Rousseau, then you can see we do not pay a lot of becoming worse when there is no contamination for these methods. They are still also quite good when there is no contamination. Of course, you pay a little bit, but under the outlier situations, in the outlier situation, then those procedures are better than the original SIR. So keep the, I think, splendid idea of SIR, just robustify it a little bit, and you can still make use of SIR, even when there are a few large outliers in the data. And of course, one could say, well, this is just worst case considerations. Yes, it is worst case, but as we have seen in these microarray data, it does happen sometimes that there are really strange outliers, and when one does dimension reduction, maybe one should take care of this aspect. Okay, so now to the second part, where we look at the special case of dimension reduction, which is variable selection. That is the same type of model, but now we only look at coordinate projections, because this is just variable selection. And in that situation, the estimation of the dimension reducing space B is just the task of finding the subset of the true predictors. Now, there is a method called EARTH, which has been recently suggested by Hel Doxum and his collaborators. I think he even introduced it at your birthday workshop in Princeton 2 years ago, and since then we are discussing on this. Well, why EARTH? This is also a nice acronym. It's called EARTH because Mars is around, okay? And as you might expect, Earth is a little bit more down to earth than Mars is. And so, in fact, Earth does not do the same, does not solve the same problem as Mars does, because Mars is at the same time a dimension reducing technique and estimate the corresponding link functions by such kind of spline functions in higher dimensions. So you find these knots, as you remember what Mars does, you find knots and you split up your X space and estimate the link. So Earth is only solving the variable selection part of the problem, and what Hel Doxum suggested is firstly apply Earth as a variable selection method to your data, and then apply Mars afterwards to improve the whole method. So what does EARTH do? It's an acronym for Efficacy Adaptive Regression Tube Hunting. One must have had thought quite a while to come up with this, but I like it. Anyway, so of course we are again in the situation that, well, you have some function of your predictors, and to find out whether, say, the else component of your predictors is active, you could set up such a test problem stating whether the function is constant, so it's not influenced by that component, or not. Well, of course, we have heard this already in Peter's talk already. There is a problem of confounding in solving this test problem, and also Doxum and his collaborators pointed to this problem, and they solved it as follows, namely by this what they call tube hunting. Okay, so the solution of this test problem is based then in their setting on so-called importance scores. But how are those found? Well, they let me explain this again in 2 dimensions, otherwise one can't draw a picture for this. So you have, of course, to condition. If you look at XL and want to know if that is active, you can only find out if it is if you condition on the other component. So XL is now x1 because we are in 2 dimensions. And what is done is in the other component, for some point x0, well, which is x1, 0, x2, 0, this is this point here, you construct such a tube of width delta with some distance measure d, and that is also changed within the process of Earth. So here it's just taken as a very simple absolute distance of the two, of 2 points here. And then you also have to find what is called a bandwidth size neighborhood in XL itself. And that is chosen such that the probability of the detection of the fact that XL is active is maximized. So that's a procedure which in the end gives you so-called importance scores for each candidate predictor, and those correspond to the mean tube efficacy at m points, which are chosen appropriately. I won't go into more detail here. And also the distance measures which occur, let me just go back. This is a distance measure here to do this. As you see, they can be changed within the process adaptively. Okay, and then you decide the test problem. Whenever the importance score is high enough, then you include XL as an active predictor. Okay, so that's just a very short explanation of how Earth works. Okay, so is Earth robust? Because, well, we had been interested in that question because before that we had been investigating Mars, and the non-robustness properties of Mars are quite complex. To a certain extent it is robust, but for very special contamination schemes it isn't. So we looked at Earth and we did the same thing to this method as to other methods. Well, we looked at very different link functions F. We contaminated some X points by pushing them far outside, but we have also been looking at at many other contamination schemes in Y direction, in interchanging X values and so on. This is just one of those we have been looking at. And of course you have to do this for different dimensions and sample sizes and so on. And well, as performance criterion we had chosen the number of correctly and the number of falsely selected predictors. And here I will just only show you the general result. It seemed that Earth is affected only very slightly by outliers, even if they are very large. And maybe, let me just go to something. Of course, in that situation, one is not only interested in the correctness of the variable selection, but as Earth is just meant as a, well, say, pre-screening method, after which Mars should be applied, one should rather compare Mars itself with Mars where Earth is used as a pre-step. And that is what we have done under different contamination schemes. And you might not like this one. One contamination had been just to interchange the observed Y values for certain X observations. We also looked at outliers in Y direction, and we then have been studying a couple of functions which in the Mars context are the usual suspects. They also have been tried out in Friedman's paper, and so these are functions which we looked at. So this is the contamination schemes, and so just interchanging Y values and putting outliers in the Y directions has been done here. You can do other things as well, of course. So, And that is how we did it, to replace certain amounts of the Y observations by larger outliers. Okay, so what we looked at then, we applied just Mars and Earth plus Mars to the data for all these different functions, and at performance criterion we looked at the L2 distance. Okay, so that is what can also be taken, namely correctly selected variables, but I will show you here only the L2 distances. So this is a simple function. This is the result for d equals 10 as high dimension, d equals 20, and you can see box plots here for the L2 distances, and what you can observe is that, well, the results are quite similar. There is only a very slight improvements for, well, in the case where there is no contamination, Earth plus Mars works a little bit better than just Mars. And this keeps ongoing also under certain proportions of outliers. And if you want to see all these pictures, we can shortly look at those. This is now a more complicated function, and again, in almost all situations, also when there is no contamination, Earth is somewhat better when combined with Mars than just Mars. And when there are outliers, then the robustness of Mars plus Earth is also higher. This is not absolutely always the case. There are certain situations where you do not get as much of added value when combining Earth with Mars, as also it is the case here for this function. It's can easily see these numbers, by the way, tell you how many outliers are still there. So there's also some well, there's a large variability in the Mars results. That's what one can see here also. Okay, so and here is one situation for d equals 10 where Mars plus Earth had been a little bit worse. And if you look at this function, that is a more complicated function, but this added value is lost when the dimension becomes higher. Then you are even better again when there is contamination. Okay, so there's other functions, and this is now the other contamination scheme where you put outliers in the y direction, and I don't want to bore you with too many of these pictures, just want to have a look. Almost always you get better L2 values, and so let me go back now to my last to the last part of my talk. So that has been Earth and its robustness, especially when combined with Mars. And now I would like to come to the last section of my talk, which is SIS, which stands for Sure Independent Screening, which has just been introduced in a recent article in the Journal of the Royal Statistical Society by Jian Kang Fan. And well, we have been looking at it, and it was invited. Was invited to give a discussion of this nice article. So, what is the case here? So you want to do variable selection when the sample size is much smaller than the dimension of the predictor, which happens often in life science data. Okay, so, and you are of course interested in variable selection here. That means you are looking for coordinate projections. And as a special assumption in that paper, the authors were looking at a linear model. Okay, so, and in this linear model, they formulated the aim to find the active variables such that you come up with a number of them which is smaller than the sample size. So this is a very special task, of course. You are not aiming at finding the minimal number of active predictors, but a number which is definitely smaller than the sample size, of course including the true ones. And what they have been suggesting is some kind of shrinkage method, which one could really love for its simplicity. Okay, so given the data, they, as I said, sample size much smaller than dimension. The first step, they start by standardizing the data, as that has been necessary also before, and then they just calculate the pairwise, somehow rescaled correlations, which is nothing but the covariances. Call them omega j, order them by absolute sizes, and then very simply you select that submodel, that is those indices of predictor components, such that their absolute values are among the first k largest of all. So very convincingly simple. And it is nice indeed. And nevertheless, we thought it could be even also robust when you replace within each step in this method the estimators by their robust counterparts. So use a median as location and a med or something else. We have tried out a couple of possibilities here, and instead of using the empirical covariance matrix, one could use a robust covariance matrix, namely what has been introduced by Gnanadesekan, the Gnanadesekan Kettenring estimator of scatter. Okay. So in that situation, we have been looking again at contamination schemes, at outlier schemes. This is, well, some function, and we have taken the same one than had been the one which had been used in the paper and in other comments. We have also taken the same choice as in the paper, where the true number of active predictors is just sample size -1 to start with something. And well, we just enlarged one observations, make it larger, and looked at the number of correctly selected predictors. Okay, so what happens? This is the result. So what does this graph show? Here is sample size 50. The lower board is sample size 70. Okay, so we are looking at the relative number of correctly selected variables, and in that situation it is 3, the correct number. If you like just to go back, as you can see here, should be 3. So in the uncontaminated situation, which is this one, the original cis and the robust version, rho-cis, behave as you can see here. In the uncontaminated situation, rho-cis pays a little bit. It has a somewhat smaller relative number of correctly finding the true predictors, whereas in the contaminated situation, this is, well, the other way round. The non-robust cis sometimes finds only 2, whereas now the correct number is more often found by the robust version. And this is also somehow true when the dimension becomes higher. And of course, as higher the dimension becomes, the more difficult it becomes for both procedures, as you can see here. But always in the contaminated situation, rho-cis is better. For higher dimension, it pays quite a large price for this, which has to be admitted. And so on. For larger sample sizes, this becomes, however, better the picture for the robust version of this. And that's why I would like to conclude that since dimension reduction in the context I've been treating it here, it is just used as a pre-step, as a first step, before you go on estimating the link function. And that's why it is very important that one estimates the dimension reducing subspace correctly and not influenced by contaminated observation nor outliers nor whatsoever. And that's why I think in this context robustness is also an important issue, and it seems that Dame as well as Roses are good candidates for that. Thank you.
So I think Venus is clearly up for grabs. Dave.
So I like your philosophy very much, and I have a couple of, let's say, comments or queries, just you can react how you wish. I think, so the first thing that I'm getting from your talk is that for every acronym there's another one, which has like RO in front of it, or some similar modification. And then the thought that prompts is that in practical work, people are so overwhelmed by the forest of acronyms and the difficulty of implementing anything correctly in the real world, that one thing that might hold back some of what you're advocating is people's belief in sort of the meta principle that they might take a non-robust procedure where the software has been heavily tested and people have used a lot and be more likely to have a true result come out of it than if they cast around for a new procedure, or implement it themselves, or borrow some software that they haven't seen heavily used. I've seen that a frequent objection to robust procedures. I just wonder if you have any reaction.
Well, answering to the second part of your question, yes, that is how people make use of statistical software, but also the Mars software is quite complicated to use. When we wanted to try it out to study if it is robust, we also had some problems, especially when trying to robustify it, because you can't really get into the code. So you are right. Robustifications of such methods would even look more complicated and less treatable to applicants than classical methods. Some of them are now in R, though, and can be used. So I'm somewhat optimistically predicting that the more they are available in R or so, the more they might be used. And to the first point, maybe, it's not that all acronyms with robust get an RO in front of it. Sometimes we also try to find female versions, like Sir and Dame, and that's why we had loved to come up with a robust Venus. Okay, but I interrupted you 2 times already. You wanted to respond.
No, well, I just wanted to interject. So I think the robustness community needs to think about this problem a bit more. I've seen it numerous times where I personally am very enthusiastic for these methods, but I don't think I have the right tools of persuasion, and I don't think they've been built by the robustness community for me to use. So if the community could work on that, it would really help.
Yeah, I can't but agree. You're right. But we should work on that. Thank you.
I had a question about, I guess, more on the first part of the talk. I mean, with the model you started with, is sort of there's 2 approaches. There's the forward and the backward approach. Right? The forward approach would model y given x, and you mentioned examples of that, the PPR, projective supergression. It's also neural network models use that approach. But then the SIR and all the other associated approaches use a backward approach. They require some kind of spherical symmetry of some sort to work. So I guess my question is, what's the advantage of the backward approach when the forward approach seems pretty straightforward and doesn't require the assumptions to work that the backward approach does?
Well, to use the the inverse conditional expectation of x given y, of course, makes it more tractable. But you're right. In SIR, you need to have a function which is somehow monotone or so. Of course, you can't have a like parabolit, which is too symmetric. But the more sophisticated version of these methods, which are based on higher moments, they can cope with such kinds of symmetry. But I think it's just the simplicity and also the fact that you have something, you can really have something in mind, because this conditional expectation of x given y that lives in this dimension reducing subspace, and that can be proven. So, and that was the idea behind it, Lee had.
Can you find the same subspace by doing it the forward way?
How are you doing it then? Because you are then suffering from the curse of dimensionality. This is just coping, because in the y direction there is no y dimension.
I mean, you just changed the model. I don't.
If you just change
You
this?
just talking like a, there's a set of all probability distributions of y comma x, and somewhere in the SIR literature, you said I'm going to restrict it to a subset of probability distributions where the expected value of x given y is something like linear in x. So you've made a small model, and you have a nice estimator in that small model. You could ask what's the optimal estimator in that model, what's the bound, what's the optimal rate of I mean, it's just another math problem. But you changed from a non-parametric problem to this much smaller model, right? And so but what's strange, I've heard several of these discussions. If I was giving your talk, the first thing I would have said is that we're taking a non-parametric model, we're going to reduce it. Consider estimating the expected value of y given x in a model where I give you a priori the expected value of x given y is linear in x. That's a well-posed math problem. Do it as well as you can. But a lot of times people just talk about central subspace and all this, and no one's ever said that, or whatever the actual assumption is that makes it. Because you've got to be conditional.
Yeah, it's just another perspective. I mean, if you do
It's not a perspective. It's an assumption about the probability distribution generated today. Makes the model very small and has a nice estimate. Right? Or am I missing something?
Yeah, you could also put it like this, but well, we can discuss this later. I think if you allow for everything, like maybe Mars does, for instance, or projection pursuit regression does, then you also run a larger risk of finding these adaptive splines completely wrongly, even if there is a true model, but you have no chance to get your hands on it. Like Earth is improving this already somehow, where you do pre-selecting variable step firstly.
Jamie,
Earth itself is trying to test that XL is conditionally independent of Y given all the other x's. That's a well-known problem. That's really
Well,
the rates of convergence.
Agreed.
Agreed. You can test that.
Agreed.
Jamie, I sort of go along with Ursula on this one. I think sometimes what you're saying is extremely clarifying intellectually to say what the true underlying structure you're assuming in a procedure is, and I would agree. But I've seen numerous times where people actually use very simple wrong assumptions and get better answers than people using like more complicated right assumptions. And
But they got those better answers for a real reason, if they're generalizable.
Yeah, I mean, it's usually like
it's
usually like a curse of dimensionality thing going on. Like the true model is. So, for example, like this, you mentioned it previously, I think, the ignored covariation among the predictors, right? That's quite frequent, and it can be can be shown to be a wrong assumption, but often you get better answers by doing that.
Well,
right, but that wouldn't mean that you want to mathematically try to understand it, make it explicit, and if it's wrong, this is how wrong it can be to get this kind of answer. It was wrong really far in this direction. You could try to understand it rather than just run a computer program. Yeah.
May I conclude with Peter's word? It seemed to be a trade-off problem.
Any further comments, questions? Peter?
Yeah, I mean, I think I also agree with it, but it seems to me that if the formulation about, which is basically a semi-parametric formulation, saying that the conditional distribution, if you equally well frame it, the conditional distribution of y given x is only dependent on those guys. So somehow that suggests that one might think of, well, as projection pursuit does. I mean, think of it as, you know,
Yeah.
dimension one.
Yeah,
Doesn't
it's-
specify with the dimension.
Right.
So you can start out, you start out with the simplest explanation, which is that the model is a one-dimensional model and then two-dimensional. The economists do that actually when they have these index models.
Exactly.
So there is, I think, the other approach is also.
Yeah. Yeah. If you have got a single index model, everything becomes much simpler, and then I might not even use something like this.
But they also talk about multiple index models,
Yes.
and then you're essentially in this game.
Yeah, both might have their advantages. To drive through the X space by projection pursuit, finding the directions, and at the same time always estimating the link. That's, I think it's another approach.
Okay, well, let's thank Ursula again and great.